Yes, so, well, I'm just to present myself, I'm a postdoc at the Observatory of the Côte d'Azur in Nice, working on interferometry and exoplanets. So, exoplanets, where do we stand today? We have detected over 5,000 exoplanets using various methods. You see on the figure all the detected exoplanets with their mass as a function of their semi-major axis. And you see that many were detected using the transit method, but also the radial velocity method. And there are also big exoplanets far away from the star that were detected using imaging. And with all this diversity of exoplanets, we can see that many features appear in this diagram. There is a lack of continuum on the part between the transit and the other methods used to detect exoplanets. There is what we call the Fulton gap for small exoplanets, which is also called the evaporation valley, and which separate two types of rocky exoplanets. And there is also this desert, which could be an observational gap, because this is a part where all our current method to detect exoplanets is not very efficient. So the detection of all these exoplanets raises several questions. First, what are these exoplanets composed of? What is their nature? Are they rocky, gaseous, etc.? How do they form and where? Do they migrate? How do they form in protoplanetary disks? So with all the observation of disks now, we can bring some elements of answer, but we don't have all the answers yet. Of course, are there exoplanets in the habitable zone, which is the place far from the star where if there was leaking liquid water at the surface of the planet, it would be, if there was water, it would be liquid. But it doesn't bring the habitability. I mean, it's one condition. So, well, it's also a vast topic. And of course, is our solar system unique? And to answer all of these questions, we need to probe many systems, even more than what we have now, and also to characterize them very precisely. So, as I said, the transit method was used to detect the majority of the exoplanets. And actually, what we measure when we use the transit method is a flux. And when the planet passes in front of the star, the flux decreases. And actually, this decreasing of flux is proportional to the ratio of the planetary to the stellar radius. So if we detect a transiting exoplanet, we need to know the stellar radius to be able to derive the planetary radius. So this method is currently used with a TESS satellite, which is on sky currently. And there is a big mission which is called Plateau, which will be launched in a few years to detect also a lot of exoplanets and hopefully terrestrial exoplanets. There is also the radial velocity method, where we measure the gravitational response of a star and a planet orbiting around the gravitational center. And again, what we would measure using this method is actually dependent on the stellar mass. So again, if you want to know the planetary mass, you need to know the stellar mass and also the inclination of the system in this case. So again, we have the dependency on stellar parameters. Even using direct detection method like direct imaging, we need to know some stellar parameters. So there have been a lot of detections now using direct imaging, using mainly SPHERE and GPI. It's really convenient to detect exoplanets far from the star and massive exoplanets. What is also really useful is that we can get the spectrum of the exoplanet. And you see on the right that to be able to use the spectrum, we we need libraries of spectra and also stellar parameters, and in particular the age of the exoplanet. So once we have all these parameters like the planet radius, mass, we can say if the exoplanet has, for example, a solid core and mantle, if it has volatiles like an atmosphere, and actually using model we can exclude compositions of this exoplanet. We can add also other stellar parameters like the metallicity, which also will be useful to exclude some parameters. So actually, when we want to derive the internal composition of exoplanets, we infer them from models, and the more stellar parameters and planetary parameters we add into the model, the more we can exclude. So, for example, if there is gas, an atmosphere, we are able to know when it was formed because we know if it's a primary or secondary atmosphere. And another example is if there is ice, we know where it was from, beyond or inside the snow line, for example. So there are many parameters like this who can tell some indications of the condition of formation and of course of habitability of the exoplanet. But the problem is that, of course, the models suffer from degeneracy. So again, we need a lot of parameters to be able to constrain the internal composition of exoplanets. So I talked about the habitable zone, and again, it's dependent on some stellar parameters, namely the effective temperature and also luminosity, because we need to know the amount of irradiation that the exoplanet receives, and it will depend on the star, of course. The hotter it is, the furthest away you need to know to have liquid water on your surface. So this is for the stellar parameters and the link with exoplanets, but knowing all of this allows also to link the occurrence of exoplanets and the star. In 2005, Valenti and Fisher showed that there is a dependency on the number of exoplanets around star according to their metallicity. Actually, that was predicted since the years 2000, I think, by Ida et al. Because it was predicted by models, because you need to have material on the disk to be able to form exoplanets. So you need metals. But there are also other links like that. For example, the planet occurrence as a function of the stellar temperature, or also the occurrence of the planets with a specific radii. And we know that there are more planets around more massive stars, for example. So the stellar parameters drive our knowledge of exoplanets, be it with direct or indirect methods. We need stellar parameters. And of course, according to the method you use to detect exoplanets, you will need different stellar parameters to constrain your system. You can also use models, but we know that they can be degenerate, and also the more you add stellar parameters in your model, the more accurate it will be. So this is the context, and interferometry can help in two ways for this. First, the characterization of stellar hosts, and for the detection of exoplanets. So let's start with the characterization. I think the most straightforward parameter that can be derived with interferometry is the angular diameter. So you know that by measuring the modulus of the visibility, we can get the size of the star, so the angular diameter. And if we know the distance to the star, we can derive the stellar radius. So this is really convenient, and it's been done for many stars now, using different interferometers on the CHA-ray or the VLTI or others. Knowing the angular diameter also allows to know the effective temperature of the star. So for this, you need to have the photometry of the star, and you combine it with the angular diameter to derive the effective temperature. So it's also something commonly made for stellar physics. Something that is more difficult to do is to derive the density and the mass of stars. So usually, it's very difficult to have a direct estimate of the mass because except in a specific context or specific system, you don't have, I mean, it's not possible in a binary, for example. So when you have a planetary transit, actually the light curve can give you information. So you need to have some parameters of the light curve that you will combine with the third Kepler law, and you will end up with a stellar density. So that's been highlighted by Seeger and Mann-Lorentz in 2003. So you need a transit. You cannot apply this to every system, but for this system, you can have the stellar density. And if you can also measure the radius with interferometry, you have a direct estimate of the mass, which is really convenient. And actually, we apply that to a few systems, so which has transiting exoplanet and that we could observe with interferometry. Making some computation, we calculated the probability density distribution function of the mass and radius of the planet, which depends on some star parameters like the mass and radius, and of some parameters of the observation of the transit and of the radial velocity measurements. So you need both, you need transit and radial velocity measurements. But having this correlation between the radius and the mass, avoid to have a density which would not be in agreement with the radius and the mass. For example, on the top diagram, you have the distribution of the density for two exoplanets which are transiting their host star. And you see that the correlation is not very high. So that is due to the transit depth and the K parameter of the radial velocity measurements, which are not very precise. But another case, which is a 55.3e, gave much better results. So on the bottom right, you see a high correlation between the radius and the mass of the exoplanet. So we really narrowed down the possibilities of density knowing the radius and the mass of the planet, sorry. On a previous estimate, we had a low correlation because the transit depth was not known very precisely. And if you don't calculate the correlation and the PDF, so you have no correlation, and you see that the density with the correlation doesn't correspond to the density with the correlation. We added in this example other parameters in our models, and you see on the left that you can infer different densities according to what you put in your model, actually. So the best estimate with the best correlation in yellow is a model where we put all the good parameters inside. So we would like to apply this method to many other exoplanet host stars. So this is one of the aims of the Spica instrument. So I encourage you to see the talk by Denis Mouard later in the week. Another example is where we applied the same method is the one of HD 97658, where we could also compare the mass, I mean the parameters of the exoplanets, but in particular the mass, which we found higher using the direct method than using the model. So it's, I think, very important to do that when we are able to, because if we had a big survey of stars hosting exoplanets where we could derive the mass of the star and of the planet, of course, it would be very useful. also to derive other parameters like the age, because we could refine stellar models like that. When you see on the right different estimates of the age of a star using nephron method, and when you know that to derive the composition or just to know the nature of exoplanets, you need the age, but it will be really interesting to refine that. Another example is a CO2b, where you see that using models, you don't have the same results for the star parameters, and then the composition of exoplanets is different, of course. So to continue with problems, I would say for exoplanet characterization, there is a problem of lamp darkening. So it's a problem both for transiting exoplanets and for measuring the angular diameter of stars, because in both cases we fit the light curve or the visibility curve. And actually, fitting the lamp darkening laws causes biases in the transit parameters, and they can reach up to 1% for the ratio of the planetary to the stellar radii, and also a few more percent for the semi-major axis, for example. So the goal of the future missions like Plato is to derive planetary radii with 2 or 3% precision. So if you already have 1% precision lost because of that lamp darkening, you cannot reach this goal. So in interferometry, we use different laws, and we know that it gives different results. But the good news is that measuring directly the lamp darkening is possible, and it's been done with AlphaSen by Carvela et al. And actually, they found that the lamp darkening was weaker than predicted by the model when the Earth 3D. So this is also a goal of the Spica instrument, and it will be very important to have very precise stellar and planetary parameters to have direct measurement of the lamp darkening. And finally, when it's not possible to measure the angular diameter of a star, of course, we cannot do it for every star, we can use a sulfide brightness color relationship, which is a relation that is based on the photometry of the star. And from this photometry, we derive the angular diameter of the star. So it's an indirect way to derive the angular diameter of a star, but it's based on direct measurement. So you see here that many laws of SBCR are on the diagram. And actually, there are discrepancies between the laws that can reach up to 18%. So it's really not enough to characterize very precisely the exoplanetary systems. There have been some study to refine these laws, and now we reach 1 to 2% precision on this law according to the classification of the star. But this requires good precision on the photometry. So I recommend to see, for example, the paper of Anthony Salsi, who found the laws. Okay, so that's all for the characterization. I think that we could say a lot more about that, but I will just spend a few more minutes to talk about detection. So I talked about transits and radial velocity, but with imaging, interferometry can also be useful, actually. So there are two big limitations for exoplanet detection using imaging. The first one is a contrast. When you want to detect an exoplanet close to a star, if you have a sun-like star and a hot Jupiter, the contrast is already 10 to the 4 to the 5. So detecting an Earth-like planet is very challenging. It's like trying to see a candle size to a semaphore really far away, so very challenging. So to deal with this problem, usually we use coronagraphy. So we hide the star, and then we can see the exoplanet. The other problem is a resolution. having 1 milliarcsecond resolution is equivalent to try to detect two pieces of 2 euros seen by the slide from Nice, and the pieces will be in Britain, so also very challenging. The stellar diameter has the order of millisecond of arc for transiting exoplanet host stars, and it's a bit more for the separation between the star and the planet. We go to a few mass to a few arc seconds, so we need interferometry for that. Using direct imaging, there were predictions about the detection of exoplanets, and you can see here on the left what was done with NACO, which was the previous instrument before SPHERE for detecting exoplanets, and the expected detection using SPHERE within the SHINE survey, which is the survey dedicated to exoplanet detection. And on the right, you see that we didn't really detect exoplanets precisely where we expected to do that. Also, on the bottom, you see the limiting contrast, the detection limit, actually, using one of the two instruments of SPHERE, one of the three instruments, which is IRIS. And you see that really close to the star, so at less than 1 arc second, the contrast that you can reach diminishes. So to detect exoplanet really close to the star using direct imaging is also very difficult with the current instrumentations. So one approach that can be really interesting and deal with this problem is to use the kernel phase analysis. So when you have 3 telescopes or more, you can measure the closure phase. So everybody here knows that. For each pair of telescopes, you have a measurement of the phase, which is composed of the expected phase and a piston. And all these pistons for a closed triangle made of 3 telescopes are not independent, and then you can subtract them. Then the kernel phase analysis is a generalization of the closure phase. It's actually putting in a matricial form all the phases, and then by computing phase transfer matrix and the redundancy matrix, you can project your closure phases into a subspace which is untouched by residual aberration. So with this approach, you don't need a coronagraph. It shouldn't be saturated, and what is really interesting that you can probe regions which are really closer to the star. So this approach requires a discrete representation of the pupil that you are using. So here you have 2 examples for the SPHERE pupil, the field pupil, where each point represents a point of the baseline. I mean, the 2 points make a baseline. And on the bottom, you have the sparse aperture mask of SPHERE. So you can do the same, but with sparse aperture masking. And on the right part, you have the UV coverage corresponding to your pupil. So it's like a virtual interferometer that you build out of a pupil. Then here in this, there is a kernel phase data analysis pipeline that has been developed by Franz Martinach, and which is called XARA. And using this discrete representation of the pupil, the XARA package computes the kernels. So you see here a representation of the kernels on the left for a star with an exoplanet, and on the right for just a random noise just to see the difference. And from the kernels, we make a fit and compute the collinearity map, which will give us the separation, the position angle, and the contrast of the maximum signal, which correspond to the position of the companion. And we applied that to sparse aperture mask data of SPHERE for the star HD 142527. So you see on the left the pupil that was used and the corresponding image. And actually, what we find is a position and contrast really close to what was found without SAM. So it was used to validate our pipeline. And also on the bottom line of the SAM images that you can see on the right. So these are the published data from Claudia et al. 2019. You see an image reconstruction using MIRA. And if you look closely, you can see some artifacts on this image reconstruction. So with the kernel, you don't get these artifacts, which is quite interesting. And just to finish with, I would just say 2 words about kernel nuller. So the kernel nuller is an idea that was first introduced in the 80s. And the idea is to cancel the light of a star and making a modulation to find the exoplanet. So for example, if you have 4 telescopes, one bright output will be where the light comes out, and the other channels will be used to find the exoplanet. So there are the dark outputs. And during the night, there is a rotation of the interferometer, which is natural. So you will arrange the system so that the star is constantly null, and you will see a modulation of the signal to which will indicate where is the exoplanet, if there is any. So this is a work it's a research that is proceeded here in Nice by the kernel team. So this is a PhD student, Peter Chengipe here is applying this method to the VLTI. And actually, it's also the subject of many coming up instruments and missions. And I can encourage you to attend the talks of Friday afternoon because many people who knows better than me will talk about this and all the results that we can expect using this method. So just to conclude, the stellar parameters are very important for exoplanetary characterization, and for this, interferometry is a very interesting method. It can be applied to direct and indirect observational method to refine the stellar parameters. It's also very important for the detection and to deal with the angular separation, and also because it's useful to develop new detection methods. And I thank you.
Thank you, Roxanne. Are there questions in the room for Roxanne? Yes, Anthony.
Hi, Roxanne. I have a question about the kernel technique with SAM. Do you have an idea about the contrast limit of the technique?
So it depends. In this case, for example, the companion was quite bright, but it's normal because we wanted to validate the pipeline, so we need something bright. But I made some simulations, and I was able to detect companions that had a contrast of 5 to 6, in magnitude difference. So quite faint, actually. But,
okay, and which fraction of lambda over d?
In theory, down to 0.5 lambda over d.
Thank you.
So, well.
Are there other questions? I see that online we have no question at all. In the room? No. So let's thank Roxanne again.